Okay, so we've seen how we can find the derivative by the limit definition, but that takes a lot of work and is often time-consuming and very tedious. The fact is that we have a lot of rules of differentiation that allow us to calculate the derivative without using that limit definition. And that's what we're going to be studying now. These are all based on the limit definition, so you can prove them all via the limit definition, but we want to use the results of it to make our differentiation process a lot simpler. So these are basic differentiation rules, some of the initial ones that we'll start with, and then we'll learn some more. Okay, so the first is the constant rule. Okay, and this is a very important one. The derivative of a constant function is 0. What that means is, so that is, if c is a real number, a constant, then the derivative of c is 0. Okay? So for any constant, its derivative is 0, meaning for any constant function, the derivative is 0. Now this should make sense if we think about the graph. Any constant function, so if we have a value c there, that would be the function f of x equals c, or y equals c, however you want to look at it. And how is that changing? How are the y values of that function changing? They're not. Their change is 0. So meaning, no matter what x is, you're always getting the same y value. The y's are never changing, so that is a derivative of 0. Okay, so practically speaking, when we encounter this derivative, so in the examples here, so we have the derivative with respect to x of 3. Well, 3 is a constant, its derivative is 0. All right, that's using the Leibniz notation, but again, we could use the prime notation as well. So if we have the function f of x equals 10, and we ask what's the derivative, then the derivative f prime of x would be 0, again, because 10 is a constant. Okay, very easy to apply, but hugely important. Okay. The really big rule that we use all the time is the power rule. Okay, so this is dealing with powers of x. Okay, so if n is a real number, then the derivative of x to the nth power of x, is this. N times x to the n minus first power. Okay, so what we're talking about is basically how we do the derivative of any power of x. So when we're actually doing the derivative of x to the n, usually this is how we think about it. We think about the exponent n then comes down in front, like that, and then we have x, and then we reduce the power by 1. And that's how we end up getting our power rule. It seems strange, but again, you can prove it, and you can look in the text. You can prove it using the limit definition. So let's look at some common examples. All right. So the derivative of x to the third, well, that's a power, so it's 3x to the 3 minus 1 is 2. 3x squared. The derivative of x squared, well, that's 2 comes down. X to the 2 minus 1 is 1. All right, so normally we wouldn't write that. We just write 2x. All right, here's an interesting one. The derivative, this one here, the derivative of x. Well, you could think of x as x to the 1. And so what you're really getting is 1x to the 0 when I take 1 away from there. But x to the 0 is 1, so we actually just get 1. Now, of course, when I see derivative of x in the future, I'll just put 1. But I'm showing you why it's consistent with the power rule. Oh, interesting about the power rule. The power rule doesn't care whether it is a rational exponent, a negative exponent, anything. As long as it's a power, then we can use the power rule. So for this one in D here, derivative x to the 1/2. All right, so that's 1/2 comes down in front. X to the 1/2 minus 1 is minus 1/2. Okay, and what you're going to see is that with derivative taking, we often prefer one thing, rational exponents as opposed to radicals, and also we prefer negative exponents. As you can see, I'm not actually going to change this right now because for derivatives it's a fine form, but we should understand that we could actually end up converting this into a different form and have 1/2 radical x would be the same thing. But again, I'm not saying that that is the answer that we should, the way we should write it right now. We're going to see that how we write it depends on what we want to do with it. If I want to do more on derivatives, then I like this form here. If I want to plug in numbers, I'd probably like this form here. So it's all going to depend. All right, more to that point, so the derivative of x to the minus 2. Well, that's just minus 2, x to the minus 2 minus 1 is minus 3. Okay, and again, so the idea is that if this had been written as the derivative of 1/x squared, I would actually want to write it like I had it in the problem in order to get my answer. And then if I wanted to then go back and say this is instead negative 2/x to the cube because I want that form, then that's good too. But we play these games with different forms depending on what's good for us at the moment. Okay. So now we're going to go into seeing what happens with different things you would do to a function and how that relates to the derivative taking. Now, notice these are the same type of things we studied when we did limits, and they're the same type of things that you study when you originally look at how to add and subtract functions. We want to know all the rules associated, what we're allowed to do, and what order we're allowed to do with them. That's something we do for everything. We did it for limits. We're doing it here for derivatives. We'll do it later on for integrals. Very common. Okay, so the constant multiple rule, basically, I want to know that if I have a function being multiplied by a constant, and I want to take the derivative of it, could I do that in a different order? Instead of multiplying the constant times the function and then taking the derivative, could I do the derivative of the function first and then multiply by the constant? And yes, you can. Okay, this could be easily proven using the limit definition. We're not going to go into that though. So what does this mean? So this means if we look at the example, and again, some of these I'll do with a lot more work than we'll do within the future, just because we'll skip some steps. So what this one in A is really saying is that I could rewrite this as 3 times the derivative of x squared, which is then 3, and we saw the derivative of x squared is 2x to the 1, or just 2x, and then I would have 6x, and that would be my answer. Now, of course, I'm not going to usually go through all these steps in the future. What I would do is really just go from here and say the derivative of 3x squared, the 2 is going to come down and multiply the 3 to give me 6, and then I'm going to do x to the 2 minus 1, which is x to the 1. And so that's how I really do it in one step. Okay, similarly here, the derivative of 4x to the 1/2, I could consider as 4 times the derivative of x to the 1/2, or in other words, 4 times 1/2 x to the negative 1/2, or in other words, 2x to the minus 1/2. Which again, I could have looked at by saying 1/2 comes down and multiplies 4 to give you 2. And then x to the 1/2 minus 1 is minus 1/2. And that's how I could have gotten that in one step.